All right, so we have our force there. Electric force on Q is equal to M times the integral of R squared plus L squared minus big R squared. That R and that R will cancel out. So on the bottom here, I have, well, 2L can come out, and I'm left with R squared on the bottom. And then I've got that sine alpha d theta there. Well, sine alpha, again, looking at that triangle, that's little r, alpha, and theta, and big R. This line right here, I can look at it from the top or the bottom triangle point of view. So this is R sine alpha, or big R sine theta. So, oh, the arm pops back in again. Let me keep this cubed. Oh no, it's still R squared. We have two R's, so R cubed, R sine alpha, not canceling. D theta. This is big R sine theta. So I get M over 2L integral R squared plus L squared minus big R squared over R cubed big R sine theta d theta. Sine theta d theta, we have, hope I didn't erase it, there it is. Sine theta d theta is right there. So I get M over 2L integral R squared plus big L squared minus R squared over R cubed. Big R can pop out. And then I'm left with sine theta d theta, which is little r over big RL dr. There we go. It's looking better. The R is going to cancel out. I can bring the L out. And so I'm left with M over 2L squared. That cancels out with one of those, and then I'm left with the integral of R squared plus L squared minus big R squared over R squared dr. I now have, in terms of a single variable, what are the limits of integration? That distance is rho r. What is the smallest value that little r can be?
Negative infinity.
What is this distance?
L minus R.
Big R. Yeah. So the smallest is L minus big R. And the largest? Remember, our little r is the distance from our charge right here. What's the farthest we can get?
L plus R.
L plus R. So we now have a simple polynomial. It might not look simple at the moment. It may or may not. So I have M over 2L squared. And I have this integral right here. How do you solve it? do you solve that integral? It's simpler than you think.
You can just distribute the denominator around, separate them. So they're all over R squared by themselves, and then just integrate them separately.
Yeah, if I'm reading you correctly, and you're on the right track if you didn't nail it. We're basically gonna do this R squared over R squared, which is 1 plus L squared minus R squared over little r squared dr. I don't know if that's what you said explicitly, but it sounded like you were going in the right direction.
Yeah, either that or we separate the L squared and R squared, but I don't know if that.
All right, so what is the integral of 1 dr? So this is r with our limits of integration being L minus r to L plus r, plus what's the integral of this? Well, first off, L squared minus r squared comes out, it's a constant. What's the integral of 1 over r squared?
Negative R cubed over 3.
Wrong way.
Oh.
Negative r.
Or negative 1 over r. From, and again, take limits of integration L minus r to L plus r. This is definitely doable. Just need more board space. Let's see, let's do the fancy stuff here, and I've reached the end. There we go. So that first one there, so I've got this m, which I've saved on the other page, over 2L squared times L plus R minus L minus R plus L squared minus R squared times negative 1 over L plus R minus negative 1 over L minus R. Let's pick off the easy one here. That's parentheses there. That.
2R.
So I got m over 2L squared 2R plus. If we get a common denominator here, it becomes a little bit simpler. Our common denominator would be L plus R times L minus R. So this becomes L squared minus R, big R squared, times L minus R, negative L minus R, over L plus R, times L minus R, plus L plus R. Good. So we basically got a common denominator added to fractions. And what's that equal to? Or the numerator, let's start with the numerator. What's the numerator equal to?
L squared plus L squared minus L R.
I feel like you're taking the long way around on that one.
Is it L squared minus?
All right, let's highlight here. Just this piece right here, let's just start out with that.
two R.
Okay, so that's 2R. And what's the relationship between this and this? A lot of big, good math memories are coming back, I'm sure.
You can cancel out a L minus R.
And what would you be left with? You can, it's not necessarily the fastest way, but what's L plus R times L minus R?
L squared minus R squared.
Yes, they're equal. If you just got rid of the L minus R, you'd be left with L plus R, and then this would cancel out. We're assuming L does not equal R. So I'm left with M over 2L squared times 4R, which is 2M R over L squared. And now we have to bring in that M, which is over here. Or over, oh, there we go. So KQR sigma 2 pi. KQR sigma 2 pi times 2R over L squared. Oh, okay, no, we're good. I'm cutting back again. Okay. Now, I've got this sigma in here, which I don't really want, so I'm gonna go back to the original. If we assume a uniform distribution, then sigma is equal to Q sub S over 4 pi big R squared. So sigma times 4 pi big R squared is just equal to QS. And I've got that right there. That is 4 pi sigma big R squared. So what this boils down to is J hat K sub E Q times Q sub S over L squared. Give me a moment to catch up and write it down, and then we'll talk about what the implication is. All right, what's the implication?
What was QS again?
QS is the total charge on the sphere.
It just looks like the same as the other formulas.
Yes, that's basically Coulomb's law. If we are outside of the sphere, and I have a uniform distribution of the sphere, I can treat this like a point particle at the origin, and just use straight up Coulomb's law for the force between two charges, Q and Q sub S, that are distanced L apart. So if I'm outside the sphere, I can treat this like a point charge, assuming it has a uniform distribution. If I'm inside the sphere, well, the only thing that changes are my limits of integration. So my limits of integration will not be from L minus R to L plus R. if I'm here, if L is at that spot, and that just shows up so beautifully. If I am here, that's the shortest amount, which would be, so if this distance here is L, this would be R minus L, and this would be L plus R. So my limits of integration, oh, this was on the previous slide. No, I was on this one. Just do it in green. So when I integrate little r there, I'm now going from, we're down somewhere, from R minus L to, oops, wrong way. My longest value is L plus R minus R minus L. And this becomes L plus R, and this is R minus L. So that's R minus L. So first off, what is this equal to? Okay, so I now have 2L there. Over here, what is this equal to? Or to write it a little bit more logically, negative R minus L plus L plus R.
2L again.
It is 2L again. And down here, this would be R minus L. So what's the relation, what happens when I cancel this and these out?
Yeah, -1.
So what I end up with is 2L minus 2L.
0.
So if I'm inside, so if I have a shell uniform charge distribution, if I have a charge inside it, there's no force acting on that charge. If you flash back to gravitational forces, the same thing's true of gravitational forces. With one annoying exception. All right, so again, recapping, spherical shell, uniform distribution, that shows up a lot. If I'm outside, I'll treat it like a point charge. If I'm inside, I ignore it. So let's talk a little reality. I have a shell, uniform charge distribution on it. Questions before I erase?
Is everything that we're doing right now just to prove that the force
Yes.
is 0? Okay.
Because one of the things that I don't like doing in 152, I have to do it because I can't do calculus, but it's that, hey, here's the situation, here's the formula. And the advantage of having calculus is that show with a little bit more depth of here's why. A difference between physics and engineering. All right. So I have a sphere here, conducting sphere. I throw a charge onto it, uniform distribution around the outside. And then I bring a positive charge here. So this has some charge Q sub S on it, and I have a charge Q here. What's going to happen to that? We're bringing in reality to our touch of it. The sousson of reality.
Is this like a review? Or is everything here like new, or is this like a review? Like, we
This is
recently-
new,
Okay.
or it's a review of what we did at the beginning of class today. I got a positive charge all over the shell, I bring a positive charge near it, what's gonna happen?
Repel each other.
Now let's assume that they're fixed in space, I somehow magically keep them from actually moving. But you're on the right track. What's gonna happen on this sphere here? Keeping in mind what Ben just said.
The positive charges will go to the other side of the sphere.
Let's work on the wording. Spirit of what you said, absolutely right.
Shell.
No, sorry, wrong nitpick. Remember the two rules there, opposite attract, like repels, and then the other one.
Electrons will go to the side closest to.
Yes.
Q.
So, proton's not moving over there, the electrons are moving over here. So this will no longer have a spherical symmetry to it. There is a factor that pops in of 1 minus r squared over big R squared, cubed. Which accounts for the fact that the off of reality. When I did the lab that you're gonna do on Wednesday, when I did it last week, not taking this into account, I was 4 point something percent off, and taking this into account, I was 2 point something percent off. So, if you had there's a online lab that Mrs. Sasson has, the online 252 to do.
Pivot Interactive
Pardon?
Lab. The Pivot Interactive Lab?
Yes, it was one of those where they brought the sphere closest to it, and
Yeah.
you were looking at the mass, and she said to ignore